Good morning, students. Welcome back. On Electrotechnology. Just a class list. If anyone's got 29 registered students for the subject, a few three have registered. Neto's here. Kuta Ramasuri say Mai Tanga. Not sure who Tanga is. Matoso, yes. Machau, Brenton here. Kuzwayo, Hermanus, Shongwane. These have left and Aliva. Okay, looks like the number of students we have here present today, around 17 or 16 or 15 participants, and there are some one is time to join. Okay, is there any queries with registration in your class list? If there's no queries, just give me a thumbs up to proceed. Thank you. So let's get cracking. So yes, hope you guys practiced your circuits. We are gonna touch on with a nice warm-up example over here. Just a quick recap. We last left off. We were starting with Kirchhoff's laws, and I was essentially discussing what Kirchhoff's laws was. There's nothing else besides this. We just did one example, and highlighting this point, and I keep on saying you must always check with AltiSpice. So AltiSpice is the circuit simulation software you use. Although it's not part of your assessments, it's something I'd like to introduce to you for now to verify answers and to get practice with software, and as well as using it hopefully in the future when you ever might get a hold of this, you might be designing a circuit. Okay, so I'd like to start with this example. What I expect from this example is a lot of interaction, because Kirchhoff's law is a very important law. We use it quite a bit. Okay, what's happening here? My whiteboard is just, I'm just opening my whiteboard quickly. Because it's a very important concept. You use it for both AC and DC circuits. So it's good that we both you benefiting, really engaging with this kind of stuff. I think you aware, especially with the way I lecture or teach, please ensure that you are not just listening here, but practicing as we go along. This is of utmost importance, because you start putting pen to paper, your memory, and start cementing your memory. Okay, so starting with this example, so in the textbook there's exercise 2.1 that I could not find the answer. May you please provide? Just have a look at that quickly. When I see it, it's at the big circuit. See what CISO is at a big circuit. 90 volts, okay, I see it. I'll get to that. So, okay, by show of hands, who's managed to do this example? In fact, there's a reason why I'm doing this example. I'm not just doing it for the sake of doing it. Yes, Tommy. Go for it. No.
No, sir. I was just raising my hand to show that I've done it.
Okay. Oh, fantastic. Okay, so what I'm going to do with that example, we're going to do it at the end of the lecture. So let's just proceed with the concepts here, and then we'll tackle that one.
Okay, no problem.
Yeah. What you're going to essentially end up with that particular example is a 3x3 matrix, and I'll show you how to solve them, but it's fine. So don't worry too much for now. But as I'm teaching concepts, and then gradually the more challenging ones, I'm glad you came back to me, so that's great. So I'll tackle that. Okay, so the first step here, we can take loops, the properties of Kirchhoff. We can take. I'll erase it again. You can take this one loop over here. You can take a loop here, and we can take also another loop which is exactly on the outside. Is everyone comfortable with the idea of taking loops? So we have different options in terms of taking loops. Is everyone comfortable with this? Okay. Right. So great. So just quickly, what I'll do here is I'm going to take one loop on the outside, right? Well, first we've got to show where our currents are going here, right? So do you agree with me? So this one will be I1. Outcoming here is I2, and then on this side over here we're getting an I3. So another important step is to discern how your currents are flowing over here, right? That's one way of looking at it. Once that is done, you can look at your loops, and we can have over here one loop. So the loop, okay, let me just write it properly. So I'm essentially just doing the green, this is one loop. And another loop would be the blue. So I'm going to just sketch it from the, maybe going this way, if that is okay. So that's the two loops I'm going to be taking. Of course, you are able to take a whole range of loops because all the time defined is essentially the currents through each branch. So if you look at the first loop, what we have is 30 volts. So of course we're using Kirchhoff's laws here. So the EMF must be equal to all the voltage drops over here. So the first one, I1, if you agree with me, that'll be I1 times 15. So I'm going to say 15 I1. And then we're going to say plus, I think I should do that example after this while I'm doing Kirchhoff's, so that I'll do it after this, so we're in the motion of doing it, Then we're going to have I3, but of course I3 is equal to I1 plus I2. So I hope you guys all agree with me here. And I'll just say I1 plus I2, and that's going to be 12. Okay, that's the one loop. That's loop one. But before I just want to clean this up here, just want to make it all. So I'll get 27 I1 plus I2, 12, and that's going to be our first equation. Of course, we're looking to solve this simultaneously or via matrices. Is everyone happy with my first equation? Okay, no one's saying anything. I'll move on. My next loop will be within the blue one, so I'm going to call this green loop. Green. Then our next one would be so it's 9 volts equals, so in that branch, that's I2 times 9. That's correct. And then, of course, it's going through plus I1 plus I2, which is I3 times 12. Okay. Just different. No, it's fine as long as you get. Remember, there's many ways to kill this cat, yeah, which is a good thing for you and a bad thing. Okay, so once that is done, you just gotta sort this guy out for the blue. So 9 and 12 is what? So 12, it's 12 I1 plus 21 I2. Yes, that's blue loop. I hope that's correct. So I'm assuming you're happy with this. Next step. Next step, we will open up a matrix. Of course, you can solve this simultaneously. I don't know who likes matrix, who prefers matrices or by substitution. Who? You guys prefer my method? Or your substitutions? That's 27, 12. Substitution. No, I'm not going to be doing substitution, Brent. It's going to waste too much time. Can you not do substitution? Should I show it to you? That's 12, 21, and then of course this must be equal to 30 and 9. Brent, do you have any concerns here? Why do you prefer substitution?
It says I've never actually seen matrices before you do it. That's it. So I don't actually know what's going on in the matrices. And my message in chat is just saying I prefer the subs, not necessarily please do the substitution.
Okay, so I just want to have a small discussion around this. Are you on? You're still on here, right? Okay. Did you do maths 1 with us at CPT?
I did, yes.
So do you know a part of you did do matrices in maths 1, didn't you?
No? I don't know. I was there in 2016. I don't know if it changed.
No, it was always there. Okay, so Mr. Kiefer, let me explain to you something now, quickly. Matrices. Okay, so you taught normally in in high school you do simultaneous equations, right? Are you with me?
Yes.
Yes. So what matrix is? The problem with like with simultaneous equations, it's fine when you're doing maybe two equations to unknowns and maybe even 3, right? But what tends to happen in a real engineering context, you might sit with 5, 10, 15. Are you with me?
Yes.
So when they developed matrices was like that solution to that particular problem, because there's a lot of equations related to another equation. It's a lot of setup. So matrices, and the reason why I use matrices is because it's like I'm going to use the word more modern approach on how to solve like linear simultaneous equations. Are you with me? So what I'm actually doing is exactly the same thing. Yes, I'm doing exactly the same thing, but I'm avoiding all the error of substituting this into that. So essentially, it's a tool for linear algebra. If that's okay with you, does it make you feel better? So it's not like it's a new concept. It's just a better way of doing math, more efficient way. It's like, for instance, I don't know if you can understand, like, when you're doing factorization, Mr. Neto, I'll tend to, I just want to make sure the Kiefer is getting on updating software. When you start in grade 10 or something, grade 9 or grade 10, you start with factorization, right? Are you with me? Factorization, 2 brackets, finding the roots of a parabola.
Yeah, I should also warn you, I kind of did maths lit in high school. But that's...
Yeah, I see that's your problem, yeah. But basically, in grade 11, what happens is that you start doing the quadratic equation, you see, which is like it's a better way of solving those problems. So it's exactly the same as this. There's no difference.
Okay.
It's just that this is more. Because what's going to happen, you're going to see now in the next question, this one's going to do, you're going to sit with 3 equations, 3 unknowns, and you're going to do by substitution. You're going to end up with 2 or 3 pages making massive mistakes, and it's going to be to your detriment. So what I'm showing here is a more better. It's like what you showed me yesterday, basically. Like, you know, just solve for f instead. You know.
Okay.
So this is like
Okay.
a more pleasing approach, if that makes sense.
Okay, yeah, I'm looking at what you have now, and it's kind of, if I can say what I see. So the second bracket, you've got I1 and I2, and then the 27 and the 12 is in line with I2. And if I go back to the equations, I see I1 is multiplied by 27, and
That is correct. You got it.
And then
I2 is
I2
there.
is
12. It's the coefficients. Yes, that's correct. Yeah.
and then
this is
the
equal,
and then the
equal to
second equation.
Yeah. 12 and 21. You see it?
I see that, but then how do you line up the 30 and the 9 was the first? Okay, no, I see.
You got it.
Okay, so now I know how to write it out. How to write it
Okay.
out, I know how, but now then to compute it.
So now, luckily for you, I use a calculator. So normally, how are we going to actually do this? Like when we do it by hand. So you have to find out the determinant and blah, 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 blah. But fortunately for you, I'm not concerned of the math. All I want to see is your approach here. So you can show your math, but as long as you show me a matrix, I'm happy with it. So I'll show you using the calculator. Okay, so I'm going to stop doing basic concepts here. So let me show you the math. So I'll show you on the calculator. So of course you can solve it using your by hand, the matrices by hand. But myself, I'm not concerned with matrices. I've been with all the math in between. So understanding what you're looking for. I'm just giving a second here. I'll just open it up now again. I'm going to share my calculator. You might just give me the coefficients again. Okay, so I did recommend you must get you this Casio. It's of utmost importance. Just go to mode. Mode equation 1. So okay, so over here we just put in the coefficients as is. So C will be the equal from A, B will be the I1 and I2, and this will be the voltage over here. So what is I1 over here?
27.
Yes. Oh, my bad. I press something else now. What did I press? Okay, just give me a second. No, my unlock was gone. 27, yes. Then that line.
The 12.
Yes. And that's 30, right?
And then 30.
12.
Yes.
And 30, yes.
Then the next one.
That's
12.
9.
No, it's 12.
9.
No,
12.
I1 is 12. I1.
No, that was 9.
I1 is 12.
21.
And then 21. And then the voltage is 9.
I'm hearing. Yeah, that's correct. Yeah. Okay. You happy now? See? So now the calculation is programmed to solve the matrix, and all you have to click is equal, and this is going to be I1, and this guy is going to be I2.
Yes, sir.
Okay.
So, Shane, this is probably like a shock for you. I just want to write it into my the whiteboard when I go back to have these answers. Welcome to engineering. Welcome.
Can you post a download link for this calculator also?
But thing is, you need to buy yourself one.
I'm gonna get around to that also.
Yeah, because in the exam you're not gonna be using a laptop, so as easy you can get. I'll post the link for it if you need. The calculator can do it as well. But anyway, let me just get back to the answer quickly. But just remind me via WhatsApp. Okay, so we got that done. I'm just gonna share it back to the thing now. Oh, wait, where's my whiteboard now? So I don't want to get back to this kind of thing. All right. Okay, so now we have that. I'm assuming that's the right answers. Let me just quickly check. I'm on my slide. Yeah, that looks legit. So now, of course, we're going to currently each branch. So if you look at I3, what we're going to have to do now is I3 is the algebraic sum. We just say 1.234 minus 0.2 0.27666. And your answer should be 0.9957 amps. So I hope you all got that. That's a very important approach. Okay, and of course use LT-Spice to verify your thing. I mean, I can do it less than a second. Do you want me to guys to quickly do LT-Spice for you? Are you keen to see me do it? If I get 5 thumbs up, I'll do it. I'll give you 2 minutes to decide. Pulling says yes, please. Oh yes, Tristan. Are you happy with the calculator thing?
Yes, I'll just watch a YouTube video.
Okay, great. It's not that difficult, yeah. And if you need help, just let me know on WhatsApp. I'll try to assist you.
Okay, so thank you.
Fantastic. Guys, this is not rocket science. This is still child's play. I've got three thumbs up. Anyone else? We've got a few seconds left. It's very important, students. I want to say this to you, that you need to be putting in the hours. You cannot sit here, expect me to solve things for you. You need to sit down and figure things out yourself. I'm really here, one of my functions is to teach you a concept, but you have to put in the hours to make sense of it. So I got only three, so I can move on to the next sum. Rather, no one's interested in the software. Okay, no one's saying anything. Okay, so I'll do the next question. I only got three there. Okay, so let's do that question which CCE wanted. So let's quickly I just want to get that question. Where is it now? I need to find it. Okay, wait. Yeah. Where is it? Good job. Okay, I found it. Oh, thought I found it. Is this the same thing? Okay, well, I guess it's not here. Okay, I'll try and. So this is in the textbook. It's a bit messy here. It's got like a scanned version. Okay, Subasiso, please tell me your first approach. Yeah. How did you start to solve this question? Just trying to get this all right here.
You have to identify your loops and your junction.
Okay. So where did you start? So where did you start? I'm just trying to make sure this thing is not listening to me for some reason. Okay. Best I can do for now. Yeah. So guys, Kirchhoff's here, right? I would like to talk me through this. So give me the first loop, right? So what I'm trying to tell you here is that because can you see this? I2, I1, I3, right? That kind of hint is telling you you're going to end up with 3 equations. So someone give me the first loop. So ideally what you want within the loop is to make sure that you have all 3 variables within the loop. That if you actually think about the idea we've been doing the whole time, we're actually looking for all the variables within the loop. But before you do that, like I said, you're going to have to look at the currents. So if I look at the currents, in that particular loop, we have these small branched off currents there, if you can see. So if you look at this guy over here, what is this current over here? This one over here, yeah, at the junction at B. What is that current?
We can assume, sir, E4.
Yeah, no, I know, but like, what is it if you're looking at 1 and 3? Using Kirchhoff's, that's going into it, that's going into that point, that's coming out, that's going out. What is this? Wouldn't you say it's I1 minus I3?
This is 1 minus 1,
Yes.
I3.
Yes, sir.
Yes, that's what I'm trying to say. Remember, you can say I4, but the idea is what I'm trying to say to you is that we want it in terms of I1, I2, and I3. Right? This is the hardest it's going to get, by the way. If you can manage, if you can do a problem like this, you'll be okay. So if you're looking at this one here, and I don't want the normal students to tell me, the guys who's competent, tell me what one is at C. What's the addition or whatever?
That is,
Use Kirchhoff's law. Yes,
that's gonna be I3.
yes.
Yeah, is coming in I3 plus I2.
I2, yeah.
So can I write it just over here? Just I don't write in the circuit. Okay, are we happy? Okay, next
Yes,
step.
sir.
Now we
Yes,
form
sir.
that loops. Yeah. Now let's form that loops. So of course we can take loops in several places. But the first loop I'm going to take is within that first sector over here. Right? So let me just quickly do that. So I'm going to do it loop by loop. So I'm saying loop 1. So I want you guys to talk me through this loop. I'm going to start with the 75. That equals. Talk to me. Or should I just put myself here?
15 times E1
Yes,
plus
that's good. Yes.
E1 minus E3.
No, man.
Plus?
That's
Yes.
minus.
Plus 14.
14,
No,
No, it's
yes.
plus.
that's
It's in the same
positive. That's
direction.
positive. It's the same direction. It's
I1
gonna be
minus
14 times
I3.
1
Yeah.
minus
Okay.
I3. Yes, sir.
Equal to
Is that
75.
correct?
Yes, sir.
75 is already there.
Yeah.
Okay.
Okay. Right. So loop 1.
Loop 1.
Who's speaking? Is it? That's Mr. Let me just
So
quickly see here.
far, it's okay. I
Guys,
got
you
that
can't all
one.
talk together. I can't hear you guys at the same time. So who's talking here? That's Super Season. Okay, fine. We're happy with loop 1, right? Let's look at the next loop. Let's take another loop here. Let's see. Now the next loop, I'm also going to use the 75, but it's going to be, I'm going to collect that other one now. I'll show you now. I want this loop here. Let me use another color here, maybe. I urge you to. So I'm using this loop now. You need to try with many loops to understand Kirchhoff. Once you do that, so I'm using this whole loop here, A, C, H, whatever. So if I do this one, it's still going to be 75. I could have done another loop. I'm always collecting a voltage. So 75 equals, that's going to be 15 I1, right?
Yes, sir.
What's next?
Sorry, so I think I
Minus.
see where the mistake is.
E3,
So I1 15.
15.
Yeah, what about 18?
E3 plus E3, 18.
18.
Oh, you're saying E, it's I. We call it I.
Yeah.
Okay.
Plus.
And then
Okay.
Plus 16.
Plus
E2
E3.
plus E3.
16.
16, yes.
Right. Okay, let's just clean this guy up quickly. Let's add the stuff up. 15 and 16 is what? 31? It's not. 34. What is it? What's I1 equal to? Oh, my bad. No, I'm lying. I1 is still 15. This is I2 plus I3. Sorry.
Sir, yeah, I2 plus I3, yes.
Yeah. Just I was kidding. So this is 15. I2 is 16 and I2 is just 16, it seems. And 18 plus 16 is, what's I3? $34. That's correct.
34, correct.
Yeah. Can you see now? What I'm finding here is 3 equations. Three unknowns, 3 equations. Of course, these loops we can take in different ways. Now, we can sneak in a nice small loop here. I think at the 90. That looks like one way. Remember, guys, this is one approach. So please, you can take many loops here. Kirchhoff is very flexible. Let's go read here. Okay, other loop now. So loop 3. So we have 90 equals I2 12 plus I2 plus I3 16, right?
Yes, sir.
Yes, sir.
Fantastic. Okay, let's just sort this guy out. Are you feeling Kirchhoff now? Are you do you see where we're going with this? Is that 28 plus I3 and 16? Let's check that equation. Okay. I use loop 14. Okay, right. So now it seems daunting. So let's see loop 3. But I'm gonna write next to it here, so it's just easy for me to see. Open a 3x3 matrix. Mr. Kiefer. 3x3 matrix. Equal to, let's move that a bit. So for the first equation, for loop 1, this loop 1 over here, we had 15, so it's 15 for I1, 16 for I2. No. I'm going all over the place here. Did we even clean up? Did we clean up this guy here? Is this loop 1? Is this loop 2?
Yeah, loop 1, we're gonna get 29 I1.
Oh, thank you. I didn't clean up this loop. So it's 29 I1 minus
14 I3.
Yeah. Sorry about that. Yeah, I completely forgot to sort that out. Okay. Yeah. Sorry about that. Sorry. Okay, so I1 is going to be 29. And in this case, we don't have an I2, so it's 0. And then we have minus 14 for I3. That's going to be equal to 75. Okay. Then if you look at I2, it's also equal to 75, but then I1 is 15, I2 is 16, and 34. So guys, remember your signs are very important. If you look at this over here, it's equal to 90. This is equal to 16. This is equal to, what's this, 28. And I1 is going to be, what's I1?
0.
Exactly. We've got a 3x3 matrix here. Now, normally you can solve by determinants. You can use Kramer's rule. But fortunately for us, we've got a nice calculator. Calculator is going to help us solve with 3x3. So you might think, oh yes, Mr. SCO is helping me solve, but it means I can challenge you. because you have tools to solve these sophisticated problems. Okay, so we're going to input this into our matrix now. I just want to share my calculator quickly. Super CISO, are you happy? You think you're ready for Kirchhoff?
Yes, thank you.
Great.
I get it.
So we go mode again, equation, and we choose number 2. And number 2 is a 3 by 3 matrix. So this is as much as we're ever going to get in terms of 3 equations, 3 unknowns. Of course, in real life, you can end up with some big messy stuff. So let me just quickly see here. What's our variables over here? 29, 0, 14, and that's equal to 75. If I remember correct. Next one is 15, 16, 34. Oh, let's take it 34. 75, 15. Number 3 is 0, 28, and 16. And that's equal to, what's it, 90. There's no, I think I must have a negative sign. There's a negative 14 or I have it there. Okay, so I think my matrix is right. So A would be I1, B would be I2, I3, and D would be the voltage that is equal to. So I click equal. I1 is 2,573. I2 is 3,48 apparently. 48553. I'm not even sure what answer is correct here. And I3 is negative 0.47421. All in amps. I go back to my question quickly. Where is this? Whiteboard. Sorry. Of course, it's correct. That's why I'm here. That's why I'm here. And yeah, there's an answer there. That's I18, which is, if you look at I18, that's it's going. So it's telling you, I could have even said as a test question, what's going through if I said the current going through the 16 ohm resistor, what is the answer?
We're gonna, that's sum up. Yeah, it's gonna be sum up I3 plus I2, I think.
Fantastic, boss. Fantastic. Welcome to Electros. Welcome. Okay. Whatever we do, lectures is what you can expect in the exam and in the class test. So please. Okay, guys, it's time to move on to the next section. We'll be looking at the next approach to solve circuits. Right? Okay. I'll just give us a quick 5-minute break. We'll start and then 11:05. We can get back into the next theorem. So like I said, today we finish all the theorems you required for this particular subject. But I hope you found this. But so I'll see you in the next 5 minutes, guys. Cheers. All right, welcome back. Let's go back to the slides quickly, and let's move on to the next theorem. Okay, so sorry about that. Let's just quickly move along. So the next theorem is superposition, and I'll just read you a is expressed in words. It says this is again analogous to what we covered in extensive materials, where we're taking one element or one section and we're working that out, and we work on another element, another section, and then in the end we add it up. So it says here, if in any network made up of linear impedances, there should have been resistance, or containing more than one source of EMF, the resultant current flowing in any branch is a phasor sum. Okay, in this case, it's a phasor sum. This is for AC, but it's an algebraic sum of the currents that will flow in that branch. Each source are considered separately. All other sources being replaced at the time by the respective internal resistances. So basically, and the central premise of this approach is, well, what we're just doing, the strategy used in superposition is to eliminate all but one voltage or current source. So what it means is that we have different voltage and different current sources. We remove, so let's say we have 3 sources, we remove 2, we work on 1. And then we go back and then we remove 2 other 2 and work on 1. And then that's the way. So we're just breaking up the piece. It says, this using series parallel circuit analysis, determine voltage drops currents within the modified network for each voltage source or current source separately. So once the voltage drops of currents have been determined for each voltage source, the values are superimposed on top of each other and added algebraically to determine the actual voltage drops of currents with all sources active. So just like a quick graphical representation. So for instance, if you have the circuit on the left, you can see that we've got an 8 volt source, we've got a resistor there, we've got another resistor, 5 ohms, and another branch here, 3 volt, 2 ohms. What happens is, if you look at the top on the right, we first remove the 3 volt resistor, we work on that circuit, and then we get whatever currents we need, and then we go into the second one, then we remove the 8 volt side, and then we left with the 3 volt side on the right, and then we work out that, and then in the end we just sum up each the current we found in the previous one for the second one, and that's essentially what superposition is. So each approach has its own benefits, and it's basically dependent on you which approach you're going to use to solve. For whatever you want to particularly solve. Okay, so I'm gonna do an example now, which illustrates the superposition principle. Okay, so I just need to. So we'll be doing this one. This is the first example in your textbook. So what do we have here? We're trying to find the current in the 5 ohm resistor, and we've got a current source and a voltage source over here. Okay, so let's just get cracking with this. And you're going to see some interesting things once we complete this example. So this is where your voltage divider rule and current division rules are going to come in handy. This is where we're going to be using basically all of those approaches. Okay, so I'm just going to share my whiteboard again. Okay, I think that's what that looks like. Okay, so let's begin. So as you can see, we have 2 sources over here, and like I said, what we do, we first going to remove one source and then the other source. So let's see. So for the first part, we're going to say use 30 amp current source only. Okay, so if that goes, what happens now, we have a new circuit, arguably new, of course. And it looks like this. So 9.5, and we've got 9 ohms here. Okay. See, of course, you could have even used, can we use Kirchhoff here? Maybe. So here, there's no voltage source, and here we've got a 30 amp going over here. Right. So remember, the objective is to find IL, the current going through the 5 ohm resistor. That is our objective. So what do we have to do now?
Current definition.
Yes, we have to kind of reduce the circuit. And so we're going to find the current in the 5 ohm resistor now using a few tricks. The first thing we do is say those two is parallel to each other, if you agree with me. Of course, we're looking this way in. I think we can do that. That's the first step I would do. Or in fact, let's do this. I'm kind of going along the road here, but it's fine. We could have said that the 9, the 9s, we could have found there's 2 in parallel, and then we could have done current division. So let me just redo that again, like the more convenient way. So remember, guys, this 9, I'm going to resketch it over here. It's like this. Yeah, there we go. It's exactly the same. So now, again, we've got a main current coming here, and now we can essentially use current division.
Current divider, yes.
Current divider, yeah, that's correct, yeah. So we say I5 will be equal to 30 amps. Now remember, with current, we're taking the one, we down one. Now, of course, this is going to be 9 times 9, because we're going to sum that up, and 9 plus 9, and we're going to say plus 5 plus 9 times 9, and 9 plus 9. Is that correct? What answer do we get there?
Yes, sir. Let's check.
Yes, sir.
Okay, so we get 14.211. Is that correct? So now we found the current, the first current over here. Are we happy with that?
Yes, sir.
Okay, fantastic. Now we have to do the same thing now, but now we have to remove the current source. So let me maybe write it over here. So number 2, use 50 volts only. Okay, right, let's see. Oh, 50 volts source, sorry. Be professional, you know. Okay, so got a new circuit again. Oh, you know what I mean? Engineering is not easy, guys. If you're not ready for engineering, hospitality needs students. We've got 50 volts. We're happy, right? So again, we're looking for this current over here. It's not as simple as the previous one. So what we have to first do now is make this into a simple series circuit. And what we're going to do, we're going to say 9 is parallel with the 5. So that's 9 times 5 over 9 plus 5. What does that give me? Guys, it's slow.
That's 3,214.
Yes, right?
14.
Yeah, 14. Then we have a simple series circuit. And of course, we're going to find the voltage across here, right? That is the idea, obviously, so we can get the current. So that's 5 ohms, not 5, sorry. That's 3,214. It's 50 volts. So, of course, what we can do here is find, we could have also found the current if you want. It's entirely up to you the way you want to solve this. It's really, that's up to you. Because if you find the voltage across here, across this new one, remember it's you can split it up. So it depends on the way you want to do it, honestly. So maybe we can try both just to recap. So my first thing would be find the voltage across there, use voltage division, so voltage across that one. That's the one we want. And that's going to be 9 plus 3,214. And we should get voltage of 13.5 0.1579 volts across that. And of course, so just kind of zooming this guy in again, we have the 9. So remember, this 3,214 is 2 resistors in parallel. Looks like that. That's 30. So this is going to be 9 and 5, 13.1579. And of course, because this is in parallel, you have the same voltage. So the current going in the 5 ohm resistor is 13.1579 divided by 5. Right? And if you do that, you get 2,6316 amps. And I'm just going to do this for you because I like you guys. I mean, like I said, so in this case, maybe instead of using voltage division, we're going to find the current, the total current going through there. So the current going through 3,241, which is it's all the same current basically. So it's going to be 50. And you're going to say 9 plus 3,214. So this is the total current going through the series circuit. $4,0937 amps. Then of course here it's the same circuit over here, but of course I'm not going to redraw it. But then we have to use, we can use current division and then say 4,0937 times the one we don't want, which is 9 over 9 plus 5, and we should get exactly this answer. I'm just showing these different ways of actually solving this stuff. Then you're going to get 2,6316 amps. Are we happy with that? Okay.
Yes, sir.
Finally, so now we have to take this current, algebraically sum it, like I said, that guy, there is this guy. Then we have to sum them up individually, algebraically. So the I load, it's I in the 5 ohm will be 14.211 plus 2,6316. You add them up, you're going to get 16.8426 amps. If you don't believe me, go to LT-Spice or alternatively build your own circuit and see for yourself. So what do you guys think of superposition?
It's very interesting and nice.
Yes. Thank you, Mr. Mataso.
So,
Yes, Brent.
so for this method, we're using the maximum values the whole time, like the maximum voltage, and then we're working away from there. Or we use a maximum current and then working away from there.
Yes, we're using the sources rather. That's correct, yeah.
Okay.
Okay, so what I'm going to do now, I'm going to give you guys 15 minutes to do a sum. And then I'll get back to we just quickly find it. So it's one we did before. I'll show you now. I'll just move away from here. So I want you guys to use superposition to solve this circuit here. You still got two sources. It shouldn't take you longer than 10-15 minutes, but I just want to show you, I'm just trying to teach you different techniques to solve the circuits. So try this one. I'll give you guys around 5-10 minutes, whatever, to get it. And even if you look at the other previous question, we always had guy now, which we did with Civil CISO said we must do. So let me just quickly open it up. And you guys are required to know all the theorems and all the whatever I teach you, like I said. So even with this one, you can remove the 90 volt source, and then we can work out and then we can basically work out, and then we will do the 75 volt. Maybe we can actually touch on that. We'll see. Anyway, so I will give you guys a few minutes. Try using this with superposition. It shouldn't take you that long. It's a very simple circuit. Okay, guys, you can start now. Okay, students, I'm back. Did anyone manage to solve it using superposition?
Still busy, sir. In a few minutes.
No, man. I will start now. Okay, it's going to be quick. So I'm going to say use 30-volt source only. Can you mute your mic, please? From here, have a simple circuit, very simple circuit. 30 volts. So you've got 15 amps here. 9 ohms, sorry, 9 ohms and 15 ohms. Yes, and we have our 12. So of course we're trying to find the current going through our 12 ohm here. And then can you mute your mic, please? So simple. All you have to do again, you can say the 9 and 12 is parallel if you want. It's one way. And then we have a simple series circuit after this. This is 5,1423 ohms. Then we're going to say the voltage across that one. 5,1. Of course, I'm not really sketching those circuits, so it's 30 volts. But I'm assuming you guys get the idea. Yeah, 5, Pauline, can I have this answer, please? 15 plus 5,1423. What is my voltage here? From that, I can find my current going through there. In this case, that current is going to be 12. So can I have my voltage, please, across this branch?
It's 7.656.
Thank you. 7.656. Who is that, Brent or Tristan? Tristan, yeah. Okay. You got that. Then my current there should be 7. Sorry, that's volts. I'm not in amps. Yeah. 7.656 over 12. And then our current should be 0.638 amps. Okay, so that's just using the one source, right? Let's use the, what's the other source now? Use 9-volt source, I think. So we redraw this. So we've got 9 volts in the middle. We've got a 15. We've got a 9. And we've got a 12. So of course, so what is my first step? I want to see you guys over here. First step.
13 and 12 are in parallel. So
Thank you. Just checking. You cannot take this in parallel with the others because there's a voltage source over here. So be careful. 12 times 15, 12 plus 15. That's going to give me what answer?
6.667.
6.667.
Great, right? Once that is done, we can find the voltage drop again across. This is exactly the same approach again. The 6.67, whatever that is. It's 9 and 6.67 plus 9. What's our voltage source there? I mean, voltage across that. So of course I should have kept all my digits, my decimals there, but it's fine. So I think we get that. you guys agree with me. Then I do exactly the same for I5. What's the answer? What answer are we expecting here? The answer should be, what is it? What's it?
957 in total.
957, right? Okay, yeah. So then this is going to be 3,83 divided by the 12, right?
0.31914.
Yeah, 19224. Yeah. So if we add this guy and this guy,
0.957.
you see, that's why I'm here. You guys happy with that?
Yes, sir.
Okay, I'm glad to hear. Fantastic. Okay, so that's superposition, and we are essentially, okay, so I think what I should do now is maybe, because what we're going to have a break from 12 to 1, and then we can continue at 1 o'clock again, and we'll touch on Thevenin and Norton. But let me just start off with Norton, and then we can continue after the break again. Okay, so of course you're going to have to practice this. Yeah, if you have John Bird's book, chapter 15 is of utmost importance to practice all these new concepts. So now I'm going to show you a new theorem. I said we're going to finish all these theorems today. Okay. Am I sharing this? Okay, so before I just start again, just going to recap on a few things. What open circuit is, it's normally to do with voltage, and an open circuit implies that two terminals or points are externally disconnected. So what it means is that it's an open circuit essentially, right? So it's open, externally disconnected, which is equivalent to a resistance of infinity, right? That means zero current can flow between two terminals regardless of any voltage difference. The open circuit voltage is a voltage difference measured between two terminals when no current is drawn or supplied. For instance, if you take maybe a battery, right, and your battery is not connected to anything, and you put the two multimeter there, and whatever the volts of that battery, specific battery, says 12 volts, that's like the open circuit voltage. Now, open circuit things are very dangerous in high voltage situations. You touch something along those lines, you could be a resistor, but you'll fry instantly. I think your MEK electrical subject talks a lot about electrical safety. Unfortunately, I can't digress into all the applications of what's going on here, but that's important what an open circuit is, as it says. A short circuit, on the other hand, is a short circuit implies that two terminals are externally connected with resistance 0. So if you ever who has experience shorting something, you have a wire, a weak, a very thin wire, you let see the wire fry up because of all the current flowing through. This is the same as an ideal wire. This means it is 0 voltage difference for any current value. The short circuit current is a current that flows when the terminals are forced to have a 0 voltage difference. So this normally occurs when a fuse is blown, results in electrical machine damage and failure due to low insulation. Yeah, so there are those things, like when you're shorting, and short circuit is limited to current. So these two concepts we'll be looking at two things. One is the Thevenin theorem, which talks about a series circuit. If you look on the right here, a voltage source and open circuit, you'll get the idea. So it was developed by this German scientist. And I don't know talk too much about it. Yeah, well, essentially, the Thevenin, I think, it's probably French, not pronounced it right. So he developed this theorem, and I'm not going to read the definition to you because I don't think you guys will essentially remember. The idea is this, right? So if you have a circuit, you have a complex circuit, you're going to simplify it into making a basic series circuit, right? And that's the idea. So you have a complicated circuit, you're going to simplify everything into a basic series circuit, right? And then the procedure of how you're going to do it when using Thevenin's theorem, you remove the resistance, what you want to find. It's kind of like a superposition technique, right? You find the open circuit voltage, hence what I talk about the. So you basically remove the resistance, so you open the circuit, and then you find the voltage across that open branch, and then afterwards you have to look into the break. So you look into the source, and then you have to now find the total resistance of whatever the circuit is. You take that open circuit voltage, and take that resistance, the equivalent resistance, you put it into one circuit with your load resistance, and then you can find a so-called. Then you can find the resistance that you're looking for. This is a very handy technique when you're looking for specific resistance. You want to know, I want that one. And Norton has a similar approach. So Norton and Thevenin are like sister and brother in terms of the way they do it. One deals with a series circuit and open circuit voltage, where Norton will do the short circuit and a parallel circuit with a short circuit condition. So just as a quick demonstration, I want to show you problem one, and you can see over here we're going to be doing it for both kind of circuits over here. So I wanted to show you the first example, it's easy in John Bird as well, and how we're going to use Thevenin. Okay, so let's just copy this. So again, guys, this is another approach. So we'll be looking at three approaches today on how you're going to actually solve these circuits. It's entirely up to you to sit down and do the work. Once you've done a few of these, you get the idea. So should I lock this to the background? Okay. Nope, not locking. Don't want to listen today. Touching the screen. Yeah. Fine. Just get it here. Yeah, there we go. So what I want to use Thevenin's theorem to find the current flowing in a 10 ohm resistor for the circuit shown here. Okay, so what we have to do here, like I said, I'm going to first sketch my special Thevenin circuit. So I'm going to have it over here. I'm going to say it's voltage. I'm going to say V Thevenin. I'm going to say R Thevenin and R load. So the whole purpose of this game is we want to put in values into the circuit over here. Right. So the 1 to 10 ohm resistor, right? So we know this is what we want. So this is our load we are looking for. But now we need to find this guy and we need to find that guy. Okay. So first step in Thevenin, we remove the open circuit, the one we want. So now we're going to open him up. And I'm just sketching all of this quickly. So it looks like that, right? We've managed to open him up. So there's a 3, there's an 8. So that's a 5, that's a 5, that's a 5. It's an 8, and there's a 2. Okay, so open circuit. Some sounds here. Oh, sorry guys. Should have said so. Okay, So back to, let me just recap on that. My apologies for that. So that's the question. We have the green circuit, which is the Thevenin circuit. And what I'm saying is we're populating the circuit. So we know we want to find 10 ohm, right? We've got that. And of course, we did this by opening the circuit, right? Opening the circuit over here. So then we can put that over there. And now we have to find our Thevenin voltage and our Thevenin resistance, right? Okay, that's what we're doing now. So for us to find we want to find the, like I said, the voltage across this piece over here, right? First thing, is there any current flowing through this 5 ohm resistor? Did anyone give me an answer?
No,
Why?
because it's open on that side.
Exactly. So there's no current in opening the circuit. There's no current flowing. So we just essentially have this over here, right? So what we're looking for here is to find the voltage. Remember the Thevenin? We want to find the voltage over here, which will represent that voltage over there. So what we do now. So how do we find this? How do we find that voltage? What can we do? We can use voltage division, right? So voltage across the 8, because the voltage over here will be the same. It will be the same voltage there. You would say because that's now open. So that's what's this? 8 times 10. So I'm just dealing with a simple series circuit, if one could say. That's just the circuit. And it's 8 plus 2. And we get 8 volts. And that is our open circuit voltage across this break, or the Thevenin voltage. So that's going to be 8. Now what we have to do is look at the Thevenin resistance, right? So when we look at this, sketching again. So we remove the source now to find the resistance. And this should be exactly the same as Norton, 2 ohms, sorry about that. So we have 8 ohms over here. We've got 5 ohms over here. And of course, this remains open because that's what we removed. So we left with that simple thing now. And now we have to look into the break and find the resistance. So basically what it means is that we're looking this way. So the first thing, we know that so we have to find the total resistance of the circuit. So can we all find the total resistance of this? Let me just quickly make sure. It's going to be that. So remember, we're just removing all the sources here. I'm just concerned about something here. Something doesn't make sense. So look into the break and determine the resistance. I just want to confirm something. So in this case, when we're looking in, so now we have to work the other way. We have to work going this way. So that means our equivalent resistance is going to be first 2 and 8. So we're working this way basically. We have to look into the break. So you'll pick up the pattern. I'll probably give you another practice problem when we get back. So that's going to be 2 times 8. 2 plus 8. So we have to add up this way. And then we have to add 5. And then we should get a total resistance of 6.6 ohms. So that is our R-Thevenin. That's the sum of all the resistance. So it's just important to note when you're adding the resistance, you have to be very careful over here with this kind of stuff over here. So you remove that, you're kind of adding, you're looking in, but you add in the other way. I don't know why they actually say looking in, but we will get more practice on how we do that. Then we have this value, we put R-Thevenin over here, 6.6. Of course, you could have solved this using another approach, but this is the Thevenin approach. It's a series circuit now, and all we have to say R, the current going through the load, it's going to be 8 volts divided by that, so it's 10 plus 6.6, and that'll be 8 over 16.6, like nearly a half or something. So 0.481927 amps. So that's the Thevenin approach, basically in a nutshell. And so this is just a quick demonstration. So just what's important is how you're going to sum up your resistance. So normally you're going to sum up, I don't know how to say look into the break, but you will probably figure that out otherwise soon. You'll make more sense. But then you have to add up the resistance going that way, or away from the break in a way. So this is Thevenin. So guys, just take a break till 1, and then we can continue with this. So I probably have, I'm probably going to do 2 more practice problems on Thevenin, and then we will do Norton's afterwards. Okay, then I'll see you after lunch. Thank you very much.